A cosmic clash: relativity versus quantum mechanics. Our understanding of the universe rests on two pillars: general relativity and quantum mechanics. General relativity, conceived by the brilliant Albert Einstein, reigns supreme in the realm of the very large. It explains the force of gravity that governs the motion of planets, stars, and galaxies. Quantum mechanics, on the other hand, holds sway in the microscopic world of atoms and subatomic particles. These two theories, while incredibly successful in their own domains, have a fundamental incompatibility. They seem to speak different languages when it comes to extreme conditions, like the heart of a black hole or the very first moment of the Big Bang. This clash of titans is a major headache for physicists. It suggests that our picture of the universe is incomplete. A more fundamental theory, one that harmonizes the laws of the big and the small, is desperately needed. Enter string theory, a bold and elegant attempt to bridge this cosmic divide. String theory, at its core, is based on a simple yet radical idea. The fundamental building blocks of the universe are not point-like particles, as conventionally thought, but tiny, one-dimensional objects called strings. Imagine these strings as incredibly small, vibrating strands of energy, much like the strings of a musical instrument. Just as a guitar string can produce different notes depending on how it vibrates, different vibrations of these fundamental strings give rise to the different particles we observe. An electron, a quark, a photon, all could be manifestations of the same basic entity, a string vibrating in a particular mode. This elegant concept has the potential to revolutionize our understanding of the universe. It suggests a deep interconnectedness between all forms of matter and energy, a cosmic symphony orchestrated by the vibrations of these infinitesimal strings. One of the most mind-bending aspects of string theory is its requirement for extra spatial dimensions beyond the three we experience in our everyday lives. We are familiar with length, width, and height, the three dimensions of space. However, string theory suggests that there are additional dimensions curled up at incredibly small scales, beyond the reach of our current instruments. Think of a garden hose viewed from a distance. It appears as a one-dimensional line, but upon closer inspection, we see that it has a second dimension, curled up in a circle, the circumference of the hose. Similarly, string theory proposes that our universe has extra dimensions, compactified or rolled up at sizes smaller than an atom, hidden from our macroscopic view. These extra dimensions, while seemingly bizarre, are crucial for the mathematical consistency of string theory. They provide the necessary breathing room for strings to vibrate in all the ways required to produce the diversity of particles we observe. String theory's most ambitious goal is to provide a unified description of all fundamental forces and particles in the universe. Currently, physicists describe four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each force has its own set of mediating particles and governing equations. String theory attempts to bring all these forces under one theoretical umbrella. It suggests that all forces and particles arise from different vibrations of the same fundamental strings. Just as the vibration of a single guitar string can produce a variety of notes, the different vibrations of strings in string theory could give rise to all the forces and particles we observe. This unification, if achieved, would be a major triumph for physics. It would fulfill Einstein's dream of a theory of everything, a single, elegant framework that explains the fundamental workings of the universe at the deepest level. Despite its elegance and potential, string theory is not without its critics and challenges. One of the biggest hurdles is the lack of direct experimental evidence. The strings, if they exist, are far too small to be detected by our current technology. The energy scales required to probe the realm where string theory's predictions become significant are far beyond the reach of even our most powerful particle accelerators. Another challenge is the theory's complexity. String theory is notoriously difficult to work with, and deriving testable predictions from it is a formidable task. This has led some critics to argue that string theory is more of a mathematical framework than a scientific theory, as it currently lacks the ability to make concrete, falsifiable predictions. Despite these challenges, string theorists remain optimistic. They argue that the theory is still under development, and new mathematical tools and experimental techniques may eventually bridge the gap between theory and observation. To grasp the essence of string theory, imagine a universe where the fundamental building blocks are not tiny, point-like particles but rather minuscule, vibrating strings. These strings, much like the strings of a cello or a violin, can vibrate at different frequencies, and each vibration pattern corresponds to a different particle. An electron might be a string vibrating one way, while a photon might be the same string vibrating in a different mode. Now picture our universe as a grand cosmic symphony, with these tiny strings as the instruments. The different vibrations of these strings create the different notes, the different particles that make up everything we see and experience. The forces that govern the interactions between these particles, gravity, electromagnetism, and the nuclear forces, are like the harmonies and melodies that emerge from the interplay of these vibrating strings. Furthermore, imagine that our universe has more dimensions than we perceive. Just as a garden hose appears as a one-dimensional line from a distance, but reveals its cylindrical shape upon closer inspection, our universe might have extra dimensions curled up at incredibly small scales, hidden from our everyday experience. String theory, while still a work in progress, represents a profound and tantalizing quest for a deeper understanding of the universe. It offers a glimpse into a realm where the seemingly disparate worlds of the very large and the very small merge into a harmonious whole. It challenges us to expand our imagination and embrace new ways of thinking about the fundamental nature of reality. While the jury is still out on whether string theory is the ultimate theory of everything, it has undoubtedly enriched our understanding of the universe and inspired generations of physicists to push the boundaries of human knowledge. The quest to unravel the mysteries of the cosmos continues, and string theory, with its elegance, ambition, and potential, remains a beacon of hope in this grand intellectual adventure. Let us continue to explore, to question, and to dream of a future where the secrets of the universe are revealed in all their beauty and complexity.